Okay, there are people asking for the YouTube link. Alright, so let me share the YouTube link then. Alright, so the YouTube, okay, Devgati also has shared, thank you. Alright, so you can, so I hope you can see my screen. Alright, so what we have dealt so far is this long wavelength phase fluctuations. So this has sort of, this will have a typical wavelength which is much larger than the lattice spacing. You might have a superposition of many wavelengths, so many K vectors, but that doesn't matter. You still, these are still long wavelength objects. And here in this long wavelength phase fluctuation, this quantity, this is finite everywhere. But then you could also have something else, which are called vortices. Now this, we'll see what is the connection between these vortices in XY model and in superconductor in a minute. Maybe you can already see through it, but right now these are the vortices in a XY model. So vortices in a XY model, is, I think, trying to draw it is a pain. So let me see if I can just project it. Yeah. Okay. You can see my screen.
Yes, sir.
So you can see these are long wavelength phase fluctuation, and here my this quantity grad theta is finite everywhere. However, the other kind of phase fluctuation that I can have is what I am showing here. Now, this object here, wherever you see this red point or you see the green point, let's say here or here, this is where I have a vortex. Now, what does it mean? Around the vortex, the grad theta modulus goes as 1 by r. That means at the center of the vortex, grad theta is actually infinite. All right, in the continuum model. The other mathematical thing, so what you can see, it is as if the spins around this vortex is winding around it, around this point, which means that if you take this line integral, grad theta dr, and you take this over this contour, which means that you keep on adding the twists, the angular twist of each spin, each successive spin. Then when you make a full circle, you will get either 2 pi or minus 2 pi. Okay? So this kind of object is called a vortex. Now, this is a very different kind of excitation, and this is a topological excitation, just like the domain wall in the 1D Ising model that we have done before. So, just like in the 1D Ising model, we have calculated the energy of the domain wall and then the entropy. Let us do the same thing here. So, what happened? Okay. Okay, so let me go back to my OneNote. Okay, so we have seen that a vortex, if I take this contour and grad theta dr, then I get 2 pi or minus 2 pi. So plus minus 2 pi. So what would be the energy cost of a vortex? So suppose I have a vortex here and I take a contour which is center, which has the vortex at the center. Then from symmetry, all these points are roughly the same. So this contour I can write as grad theta. If this is r, I can write 2 pi r. This is equal to 2 pi. Well, plus minus 2 pi. So let me put modulus here. So which means that modulus of grad theta is 1 by r. All right. If modulus is 1 by r, then the energy, I know from the expression of the Hamiltonian, it is Js by 2. And then I will have the integral here. So grad theta mod square, which is 1 by r whole square. And then I have to take an area integral d square r. So that is 2 pi r dr. And then the limit will be a, the smallest length scale in the problem, to the largest length scale in the problem. Now I am taking a and I am not taking 0, because in any real system you will never have the grad theta which will diverge. For example, if this theta is the phase of the superconductor, you know that grad theta from Ginzburg-Landau is proportional to the current density. And the current density is not something that can diverge. If it diverges, then you will have infinite kinetic energy for the Cooper pair and you will destroy superconductivity. That is how you have a vortex core. So when the kinetic energy is enough to break the Cooper pair, you get a normal metal core. Okay, we'll come to that. But for the time being, let's continue. So therefore, this will give me Js pi log of L by A. All right. What is the entropy? Now, I could have placed, if A is my lattice constant and L is the size of the system, then I have the total number of sides is L by A whole square. So therefore, the vortex can nucleate in any of L by A squared sides. That means that the entropy will be k log of L by A whole square, that is 2k log L by A. And therefore, the free energy, which is E minus Ts, becomes Js pi minus 2kt log L by A. Alright, so I think with this now I can go back to the presentation. Anyone who has not followed anything here, this is the time to ask. This is all very straightforward mathematics. Alright, so let me go to the presentation. Alright, so now you see you have the free energy is E minus Ts. So what is going to happen when I am at a temperature which is less than Js pi by twice k? This prefactor is positive, and if I try to create a vortex, I am increasing the free energy. I am increasing by a very large amount because if I have a macroscopic system. So therefore, there will be no vortices. But as soon as I exceed this temperature, I will suddenly have lots and lots of vortices. And the moment I have lots and lots of vortices, I will destroy my magnetization, so the order will be destroyed. So I will have again the magnetization, which will look like this, just like what we have seen for the 1D Ising model with 1 by r square interaction, and therefore the order will be lost. Okay, so now the question is, why do I care about this in a superconductivity course? The reason is obvious. The reason is that you have derived the phase only Hamiltonian. So let me go back. You have already derived this. So let me just remind you. In the XY model, what we have is a spin system, and this is my Hamiltonian, where I have shown you that you will get a phase transition where your magnetization will abruptly drop to zero. However, the phase transition is not a first order phase transition because there is no discontinuity in the free energy of any kind. Now, if I am considering a superfluid, that superfluid could be either superfluid helium, which is a liquid with zero viscosity below 2.1 Kelvin, or it could be electrons in the superconductor, which is also a superfluid. So we know that in Ginzburg-Landau we can express it like this. Okay, this is just a difference in notation. This delta, do not confuse it with the gap. It is just that sometimes the Ginzburg-Landau order parameter is written like this. But what is important is that you know that the Josephson relation tells us that the velocity of the superfluid is given by h cross by 2m grad theta. So therefore, if I want to find out the kinetic energy of the superfluid, that will be half mv squared per electron into the superfluid density integrated over the, so this is for a film. So Kosterlitz-Thouless happens in a two-dimensional system. So I am considering now a superconducting film, and this is why I am taking the area integral. Now this ns, the way it is defined here, remember that this ns is actually the superfluid density per unit area, not per unit volume. Okay. So now this is the Hamiltonian for the phase only Hamiltonian of the superconductor. And you can see in two dimension this, the XY model, 2D XY model Hamiltonian and the phase only Hamiltonian for a superfluid is exactly identical. So therefore, in a thin superconducting film, I should also have the BKT transition. Any question? Because if there are no questions, I'll now go to experimental data.
Hello, sir.
Yes.
Can you please repeat why it needs the BKT?
Have you understood the BKT transition in the XY model?
Yes, sir. It is due to this. From this last class, I understand.
Exactly. So if you have understood the BKT transition in the XY model, you can see that this Hamiltonian for the XY model and this Hamiltonian for the two-dimensional superconductor are identical. Okay. The only thing is that in this Hamiltonian, the theta corresponds to the angle. Theta corresponds to the angle that the spin makes, and in the superconductor or the superfluid, theta is the order parameter, is the phase of the order parameter. So if you want, it's a quantum mechanical phase of the Cooper pair. That's the only difference. But the form of the Hamiltonian is exactly identical. So if you have the same form of the Hamiltonian, then they should undergo the same phase transitions. This is how we do mapping of problems in physics. Any other question?
Yes, sir. I got it.
Okay. If not, let me go over to the data. The first spectacular validation of the Kosterlitz-Thouless transition came from experiments on superfluid. So on superfluid helium. So helium, you know that at 4.2 Kelvin, it becomes a liquid. Kamerlingh-Onnes actually got his Nobel Prize for liquefying helium. He did not get his Nobel Prize for superconductivity. Okay, so, but below 2.1 Kelvin, or I think 2.2 Kelvin, liquid helium undergoes another phase transition, which is called the lambda transition. And at this below 2.2 Kelvin, so that's the equivalent of a Bose-Einstein condensation. And when this Bose-Einstein condensation happens, it goes into a phase coherent state, and therefore it loses all its viscosity. So helium becomes a fluid which has zero viscosity. And that zero, when I mean, it is as zero as the resistance of a superconductor, which means absolutely zero. Okay, so now what these gentlemen had done, this Bishop and Repi, they had very, very interesting experiments. And the way you measure viscosity is that normally you take a drum like this, and or you have these discs here, and you dip it in liquid helium, and the discs, they are hung by a thread, so you put it into oscillation. So they rotate like this, like the one, like this. So you put them into rotating oscillation. They are hung by a quartz thread. And the moment you undergo the normal to superfluid transition, the viscosity goes to zero, and because the viscosity goes to zero, the frequency, the resonant frequency of the oscillator changes. And from this change in the resonance frequency of the oscillator or the time period, you can actually correlate and find out the superfluid viscosity of the superfluid. Okay, actually from the time period, you can get the superfluid density. And this is for a three-dimensional superfluid. This will not have Kosterlitz-Thouless transition. So what this Bishop and Repi did was something very interesting. They took a drum like this, and on this drum they put mylar tape. Mylar is some form of a mylar is that mylar can absorb helium. So you absorb some few monolayers of helium on that, and you then cool the whole thing, and you measure this torsional, you measure this oscillation. So it's extremely precise measurement. So here these many curves that you are seeing are for different numbers of layers of this helium. So exactly how many monolayers of helium is difficult to detect, but probably this is one monolayer, two monolayer, three monolayer, and so on. Now what you see is that the superfluid density is practically constant. It decreases only a little bit, and then suddenly it crashes to zero. This is your Kosterlitz-Thouless transition. So the Kosterlitz-Thouless transition in superfluid helium was very, very well established very early on. So the theory came in 1973 or so, and by 1978, the experimental validation was already there. All right. Now, there are much more fancy experiments now with cold atoms. In cold atoms, you can now have a Bose-Einstein condensate of rubidium atom, which also behave as bosons. And the advantage of rubidium atom with respect to helium is that helium, since it's in a liquid state, not a gaseous state, there is strong interaction between helium atoms. And therefore, the Bose-Einstein condensation that you gets severely modified because of interaction. You have to put in all these interactions in. And in fact, for example, Landau, great mind that he was, made a complete mistake in superfluidity. He could never recognize that superfluidity is actually related to the Bose-Einstein condensation. So, but later it became obvious that it is when people also started studying superfluid. They started studying helium-3. Now the helium-3 isotope is a fermion because it has one neutron and two protons. So helium-3, instead of undergoing Bose-Einstein condensation, it undergoes BCS condensation, which is very different. It's more like a superconductor. And therefore, when people saw the contrast, they realized that helium-4 superfluidity is related to the Bose-Einstein condensation. Okay, but in these cold atoms, these are in the gaseous state. So here the physics is much simpler, though the experiment is orders of magnitude more difficult. And here what you can do is you can take this cold atom condensate and then by interfering two laser beams, you can make an optical lattice like this which will slice the condensate. And then in between one of these, if you look at one of these slices, this will be essentially like a two-dimensional condensate of superfluid. And here actually you have to delete these images because the analysis is a little more complicated. But what happens is that initially you start from a very low temperature. Then you increase the temperature a little bit. You can see these kind of spin wave excitations. These are the long wavelength excitation. But the moment you reach 290 nanokelvin, you start seeing a completely different pattern of this kind. So this is an optical photograph of this condensate, and you start seeing a pattern like this, and this is the signature of suddenly large number of vortices proliferating there. So this is a direct visualization, if you want, of Kosterlitz-Thouless transition. However, what we want to study is superconductors. And in superconductors, things are more complicated. Because in superconductor, there are two problems. One problem is that the superfluid is not neutral. The superfluid is charged. Electrons have a charge. So these bosons are charged objects. And charged objects means that they will have some screening length. The second problem is that these are helium, for example, is a boson, and it will remain a boson till very, very high temperature, maybe the temperature of the sun or much higher, where you can actually break this. Maybe in a fission reactor or something like that. But a Cooper pair is not a boson of that kind. A Cooper pair with increasing temperature, Cooper pairs also break. You have quasi-particle excitation. So quasi-particle excitation has to be folded in the Kosterlitz-Thouless transition when you are looking at a two-dimensional superconductor. So the way you do that, first of all, okay, so the first problem which I told you, the screening problem, was considered by Kosterlitz to be very major, and in fact in his original paper he said in a superconductor you will never see a Kosterlitz-Thouless transition. But later on when people analyzed more carefully, they realized that the screening length is actually very large, and therefore often that exceeds millimeter size. So if you are at smaller sample size than that, you will see Kosterlitz-Thouless transition, and later it is realized that the charge of the superfluid will broaden the transition a little bit, but that's not a very major issue. Now the second thing is quasi-particle excitation. You know that if you measure the temperature dependence of superfluid density, then even without Kosterlitz-Thouless transition, it will vary like this. It will go to 0 at Tc. This is BCS theory. We have derived how 1 by lambda square varies within BCS theory. What will happen when you have a Kosterlitz-Thouless transition, then on the top of that, when you reach the Kosterlitz-Thouless transition temperature, your superfluid density will abruptly come to 0. So instead of this curve going smoothly to 0 like this, it will go like this, and then here it will go to 0. Okay, what do you see? So what you have to do is to measure the superfluid density in thin films, and this is something that we have already discussed long back, how to measure the penetration depth, and if you can measure the penetration depth, you know how to calculate the superfluid density using this formula. Okay, so now I will straight away go to result. So this is what you see. So I have taken a particular superconductor here, which is niobium nitride, but this the material is not so important. You will see that anywhere. So niobium nitride has a coherence length of about, let's say, 5-6 nanometer. So when you are at large thicknesses, you see that it follows BCS theory very well. But then when your thickness is smaller than, of the order or smaller than the coherence length, you see that suddenly there is a deviation and your superfluid density actually abruptly drops to 0 instead of following the BCS curve. So let me see where, okay. All right, I don't think I have a better thing anywhere. Let me see if I have something better. So this kind of transition it has been, so as I told you, here this is for niobium nitride, but you don't need to necessarily look only at niobium nitride. You can also look at, for example, this is a high temperature superconductor, yttrium barium copper oxide. Here also you see that it's decreasing slowly and then abruptly jumping down. So it's not completely vertical, it's not a complete abrupt jump to 0, and this is actually because of disorder effect. There is inhomogeneities in the sample, so you effectively, that smears the transition because you have now a distribution of Kosterlitz-Thouless transition temperature. All right, let me see if I have something. Yeah, okay. So this is what I wanted to show you. Here you can see these are the Kosterlitz-Thouless jump, and if I expand this region, you can see this much more clearly. And you can also see, I told you the coherence length is 5 to 6 nanometer, and you can see this only when you are of the order of the coherence length or smaller. Now, the Kosterlitz-Thouless transition, now there are matters of detail which I will not get into. You can also see the Kosterlitz-Thouless transition from the fluctuation in the resistance above Tc. So above Tc, the resistance get affected by the Kosterlitz-Thouless fluctuations. So you can feed the resistance above Tc and also get this Kosterlitz-Thouless transition. All right, but this is a matter of detail, so let me not get more into this. And those who have attended the second lecture that I gave on Friday, you have seen that you can also map the Kosterlitz-Thouless transition for a melting of two-dimensional solid, and that is what gives the hexatic fluid phase that I explained in great detail in Friday's lecture. Okay, so I think we are ready to stop. And any question? Okay, by the way, one of you, I saw you have put a message that you wanted a paper. I think the paper of Benison et al. Or something like that. Have you gotten the paper? Who had asked for it?
No, sir. Still now we didn't. Amit asked actually in the group.
Amit also. So you didn't get the paper. Okay, I'll send it. But
No.
why didn't you get the paper? You don't know the journal, or what is the problem?
Actually, sir, didn't find it actually in Sci-Hub. So Amit
Okay.
asked in the group. That's why
See, this is
we did.
the paper for Andrew reflection, the direct proof of Andrew reflection.
Hmm. About related to NF reflection. That's why.
Let me see. Okay, I think I understand which paper this is. I'll get it. Where did you find this reference? Is Amit here?
Yes, sir.
Yeah. See the reference that you have put some reference without writing the journal name, which is the
Yes, sir. It's in physics review letter. I think that slide that you have prepared for the Andrew reflection, you have mentioned that.
Yeah,
it
yeah.
was
That's
it was somewhere there.
Yeah,
yeah.
yeah.
Okay. 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 I'll find out and let you know. I'm not. I'll have to check which one that
Yes, sir. Yes, sir. Please.
was. I'm not finding it here directly. Okay. I'll send it by tonight.
Okay, sir. Thank you.
Okay. So any other question? Any other
Sir,
question?
the direct point contact, the directional contact spectroscopy and the spectroscopy, that part is covered in Dagger's review article. But can there any other easier resources for it, because Daguerre is somewhat
Bit
complicated?
tough.
Yeah.
Easier.
Dagger is tough bit. That's why.
I don't know. You can look at Gautam Sheet's PhD thesis.
Yeah, we have.
Okay.
But the
But
directional
that
spectroscopy is not
whether
not there.
directional contact spectroscopy is covered there, actually I.
I think it should be. He had done directional
Directional, I
point
guess no.
contact spectroscopy.
Okay, okay,
Must be covered there. Must
okay,
be covered there.
okay. I will go
Covered.
through.
Okay, check that. If you don't find, then drop me a line again.
Okay, okay, sir. Surely. Yeah.
Directional is not there, I guess. I have tried it.
It's not there. Okay. If it's not there, I'll check and let you know. I
Okay,
thought
sir.
it should be there, but maybe it's not there in the talk that you want. See, directional point contact spectroscopy is actually it's reasonably simple. You are doing on the different directions in the real space, and the real space, different directions in the real space correspond to the projection of the reciprocal space. So you have to take the Fermi surface. If you are doing, let's say, on the 100 direction, 100 direction, if you are doing the point contact spectroscopy, that means you are projecting the Fermi surface on the let me think about it. So 001, for example, would be on the Z plane, on the XY plane, yeah. So if you are if you are doing, let's say, 100, then you are projecting on the YZ plane, and so on. So this is check in the thesis. If it is not there, then we can discuss it one day.
Okay, sir.
Okay, sir. If I read everything apart from these directional, because I don't have much more. Actually, I have gone through all other things, but these part I don't find any very good resources. At least that I can easily perceive. So. Can I leave it before Saturday? Because all other things that I can't, that I
Okay, fine.
Yeah,
can.
yeah.
So if you are not able to understand it, then leave that before Saturday, and we can do that later on.
Okay, sir. Thank you.
Okay.
Sir, I have seen that paper.
Change the what?
Yes.
Hello.
I just got that and I have put it in the group.
Yeah. I have seen.
Oh, I see. Okay.
Okay, thank you.
All right. So if there are no more questions, then
And thank you, sir.
yeah, welcome. And we'll finish the course here. So actually, I have not kept track. Now, those who are here, is everyone from TIFR or are there non-TIFR students also? Because TIFR students, I will be meeting you, except for the two who are from NCBS, not NCBS, ICTS. The rest I will be meeting you when you come. But is there anyone who is Dibbendu? Dibbendu, actually remind me where you are from?
Pune University.
Pune University.
Pune University.
Okay. Good. So let's hope in better times
Yes.
you will have a chance to visit our lab. Let me see. In the chat box, there are other people who are writing. Obro. So Obro, so just write where you are, all of you are from. By now I have forgotten completely.
Sir, I'm from BHU.
BHU. So you are finishing, you are PhD or MSc?
Sir, MSc.
So you are finishing this year?
Yes, sir.
I see. Okay, so you will be sitting for all these entrance tests in the next year.
Yes, sir.
Okay, and what about Indranil?
Sir, I am from IIT Patna.
From
IIT Patna.
IIT Patna. Okay, I see. So you are also in the final year.
No, sir, I am actually in second year. Means
I see. Okay,
Yes.
so you have still a long way to go.
yes, sir.
Anyway, it's good that you survived in the course to work till the end. I had not expected that anyone other than those who are crediting will actually survive till the end. So I'm quite happy that there are at least 3-4 who have survived, because the course initially started with the first few lectures, which were very general. And that is essentially the part that I expected many people to remain with. After that, when it went on getting more and more technical, I was expecting that only those who have a very serious stake in learning this subject will actually learn it. So the fact that you have survived with this means that you have got a skill that is quite useful and important in the future, because a lot of the theoretical techniques that you learn, like for example second quantization or Ginzburg-Landau, you will see that these are extremely general. So these are many techniques that are used very widely in all branches of condensation physics. So even if you don't remember the details, later on when you encounter those subjects, it will come back. All right, so I will sign out. And for all those who are doing the project, on Saturday we'll anyway meet with the presentation. So on Saturday we'll have an initial review of the presentation. That's the idea, Shrojit, isn't it?
So I told them that whatever the format they will put, exactly in the same format, the first review will do, so that the modification happen on that format what they have prepared.
Okay, and what time do we start on Saturday?
Sir, we plan to start around the 6:30, so there will be 4 groups. So it will take maybe half an hour each group. So maybe more.
So about 6:30 to
Yeah.
9 o'clock or
Yeah.
something like that.
Yes, sir.
All right, good.
So I asked them that all of you should be there and ask each of every group to ask questions, so that if they can defend all of your questions, then it will be more easier for them also, that they understood that problem.
Yes. Who is this? And अभी नहीं बात नहीं करो. Okay. All right. So then yes, I think that's true. All of you should be there. So it would be also fun to see what each other is doing in this video project. It's also something that is very experimental. So it will be fun to see how all of you have done. Okay, so I'll sign off now, and all the